the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Casitas College in Sacramento, California. In this lecture, I'm going to continue forward on talking about the precise definition of the limit of a function for a calculus first course in a calculus class, or first calculus course. We had just finished in the last video the true definition of a finite limit at a finite point. If you're still lost in that slightly, it gets kind of clarified here as we start going through proofs. But still, it's a good idea to go back through and watch that video if you haven't seen it. It's critical, actually, before we move forward, that you understand the bulk of what's going on. But what we're going to do now is prove limits for linear functions. Nothing but linear functions here. The reason why is because as we move beyond linear functions, proving limits gets a little more complicated, and then moving outside of polynomials in general becomes very challenging, and you have to get very creative with proofs at that point. So let's see. Let's start with this simple example. Well, I shouldn't say simple. Let's start with this example, okay? Prove that this limit is true. If you watch my previous videos, you know that this limit was the one we were working with right from the get-go. The limit as x approaches 3 of 2x plus 3 is equal to 9. That is obviously true just from the direct substitution properties, or property. However, we want to prove now that it's true. Not that we are relying upon a property that we haven't proven, but instead to actually prove this is true. So first thing I'm going to do is hop back to the actual definition here. Whenever you're doing a proof in mathematics, you're really relying heavily on theorems and definitions, not examples, but actual theorems and definitions. So in this case, we're going to assume, hopefully, that f, our function, is defined on a punctured open neighborhood, or a delta neighborhood, about 3. Okay. So, and that's because the limit as we're dealing with the limit as x approaches 3 here. And we want to show that for any given epsilon, and in fact, let me write this down over on this side. So I'm going to put this, maybe I'll put this in blue, meaning I'm going to reserve the blue ink for what we want to happen. I'll reserve the black ink for our actual proof. So let me go ahead and write this down. Now I'll stop right here in my writing just to say something. I'm going to switch up my language every now and again so that you can understand this sentence from different perspectives. It's not enough for somebody to teach you a language in like a parrot. In other words, if I say, hey, this is how you ask for a cookie. May I please have a cookie? You want to be able to adjust that language on your own. Like, hey, I'd love a cookie if you have one, right? So you want to be creative with how you say things. So another way to say we want to show that for all epsilon greater than 0, something happens. I could have rewritten this as we want to show that given any positive epsilon. That's another way of saying this sentence. So you just need to get used to jumping around a little bit in your language. So we want to show that for any given epsilon greater than 0, there exists some positive delta, it's probably going to be small, just like epsilon usually is, such that, and remember I talked about that symbolic language in the last video, so I'm not going to repeat it here. Anyway, we want to show that for all epsilon greater than 0, there exists a delta greater than 0, such that as long as the distance between x and 3 is small, how small? Less than delta, but still positive. So x can't be 3. As long as x is close to 3, we will know that our function is close to the limit 9. That is the idea. How close to 9? Within an epsilon neighborhood of it. So again, let me go ahead and remove my highlighting here and just show you that this does align to the actual definition, because the actual definition had this. As long as the distance between x and a is less than delta, a is being played by 3. That should imply the distance between f of x and L is less than epsilon. And this right here is f of x, and that is L. So my language matches up with the definition. Now, I haven't proven anything. I'm just setting this up, letting myself know where I want to go with this proof. I want to match the definition. We want to show that this statement is true. So here's the trick with this style of proof. Now, I should mention, most proofs in mathematics do not have a structure you can easily follow. Most proofs in mathematics are very creative. They involve a lot of creative thinking, a lot of out-of-the-box thinking, a lot of critical thinking, a lot of experimentation until you finally figure something out. However, most proofs that I have done, that most other mathematicians have done in mathematics, really start with you assuming the antecedent. In other words, I want to assume that I've gotten to the end result here and work my way backwards, see how I got there. That is exactly what a lot of my students wish they could do. They wish that I would give them the answers to an exam so they could work themselves backward to the question. And often that is a no-no in mathematics. However, in proofs, it is somewhat okay to say, well, let me suppose that I am actually at the end. How did I get there? Can I figure out how I got there? That's actually a great way to think about proofs. So let's look at the structure of this and identify the end of this proof. If you don't mind, I'm going to erase a few things. And in fact, now that I think about it, it might be nice to say this over on this side right here. So what I'm going to do is I'm going to go ahead and remove all this highlighting here because I want us to really focus on what's the beginning and what's the end. So the beginning of this statement, and let me zoom into it, is really tough to identify. But kind of the trick is to know what signifies the end. So most theorems, and this is not a theorem, this is a definition, but we can think of it in a very similar way to a theorem. Most theorems have the if-then structure. So the if-then structure. Well, when you see mathematics written symbolically, the stuff before the implication sign is usually the if. The stuff after the implication sign is the then. For example, I could say, if it's raining, then it must be cloudy. That would mean that rain implies clouds. If you have rain, you must have clouds. That is the beginning and end of that statement. Beginning being that it's raining, we can assume that, and the end being that we have to prove that it has to therefore be cloudy. So if you take that idea of whatever's after the implication sign is kind of the end, then I can highlight, oops, that's not a highlighter. I can take a highlighter and highlight this and point at it and just say, that's the end result. What we would call in mathematics the antecedent of a theorem, even though technically this is not a theorem, so please don't repeat that. But that's the end result. That's the end statement of an if-then. And the beginning is the stuff that happens prior to that implication. And so I'll use a different highlighter here for that. I'm going to use my tried and true blue highlighter. And technically all of this happened before the then statement. So all of that blue highlighting, I'll use blue to kind of wrap it up here. Now this is not really the best. I'll do it like this. All that stuff is the initial or beginning statement, I guess you could call it. And like I said, everything in yellow is the end result. So that's our if in blue and our then in yellow. Hopping back to the problem we were dealing with, it's really the same thing. We want to assume that somebody's handed us an epsilon. So somebody's come in the room and they said, here's an epsilon. It is our job to find a delta such that as long as x is really close to 3 within a delta neighborhood of 3, then, let me get my other highlighter color, we have the result that our function is within an epsilon neighborhood of 9. So like I said a few moments ago, a lot of mathematicians, myself included, will start at the end to see how we could get there. Such a natural way of thinking. Like you say, I've built this car and it's called a Tesla, and some other company comes along and says, I'll buy one of those. I'll look at this end result and I will rebuild my own version of it, right? That they start with the end result, they knock it off and they build their own version of it and sell it cheaply. All right. Or cheaper. I'm not sure about that. Anyhow, so here's how I'm going to do it. I'm going to do scratch work. And this is not something uncommon for mathematicians. We often start with this scratch work. It's not like every proof in the world we just happen to have memorized in our heads. That's not how it works. We look at where we want to end up and we just do some scratch work on the side. Now, depending on your professor, they might require you to show your scratch work. I require my students to show their scratch work. So off on the side, I will assume where I want to be. I want to be at this end. So I'm going to assume that I've arrived there. Assume that the distance between f of x and L is less than epsilon. Just assume that our function is within an epsilon neighborhood of L. And just so that you know what I'm talking about here, let me bring up that visual from last video. Now, this is not the function we're dealing with. This is actually 2 to the x. I could change it. In fact, maybe I should. I'm going to go ahead and change that function to be 2x plus 3. And then I have to zoom out, unfortunately, but that's what I'll do. There we go. And now you can see, all right, great. Somebody comes in the room and they hand me an epsilon. Here's an epsilon. I'm just making it smaller and wider and so on and so forth. We're going to assume that the distance between our function and our limit 5 here. Oh, I'm sorry. I'm supposed to be doing this at 3, aren't I? So let me go over to 3. So I'm going to zoom out a little bit and move this over to an x value of 3. There we go. All right. So now somebody's handed me an epsilon neighborhood here. It's somewhat large, actually. Most epsilon neighborhoods are very small, but somebody's randomly handed me an epsilon neighborhood. And I'm going to assume that I magically have the distance between my function and my limit to be less than epsilon. And so basically, if you look at it here, I'm saying I'm looking at all of these values in this curve all the way down to here and all the way up to there. I'm just going to say I have my function trapped in this epsilon window. Our job is to find out what delta is. I want to find out what that delta is right there. Mechanically, not visually, but mechanically. So I'm back here and I'm going to go ahead and say, well, let's assume that the distance between our function and our limit is less than epsilon, which basically means that the distance between our function was 2x plus 3 and our limit was 9. We're going to assume that that's already less than epsilon, that we've already arrived at the end of the story here. Now, notice if I'm going to work my way backward, just take this journey. I'm going to use my red ink for this. I'm going to start stepping backwards. Just continue this little journey backwards, and I'm wondering, how am I going to arrive at the beginning of this statement, which is actually right before that implication sign? I want to journey backwards and eventually get to the absolute value of x minus 3 being less than something. It will automatically be positive because we're assuming that x can't be 3 here. That's the major thing you have to understand, is x is not allowed to actually be at that finite point. It has to be slightly wiggled away from it. So x is not going to be 3. It's going to be slightly a little bit away from 3. But here's our goal right now, is to step backwards from this statement to somehow arrive at that statement. And what I don't want you to do is I don't want you just to memorize how I'm doing this, even though most people will, to be very honest with you. What I want you to really catch on to here is that I'm starting at the end and I'm saying, how did I get there? That's critical. So let's see, doing a little bit of our algebra, right? Arithmetic before algebra, algebra before trig, trig before pre-calculus, pre-calculus before calculus. So a little bit of arithmetic. 3 minus 9 is a negative 6. And you might not know why we're doing this. Well, it's because I have a 3 minus 9. It seems so simple to just say that. But if I look ahead now and I think, you know what? What I want to arrive at is the absolute value of x minus 3 being less than some number, which I'm going to call that number delta if I ever can find it. That's where I want to arrive at, because again, over here, if we step our way backwards on the left-hand side there, you can see that we'll step our way backwards all the way to what we want to be at, the absolute value of x minus 3 being less than delta, greater than 0. If you take a look at this bad boy right here, you can easily visualize at this level, of course, that factoring out of 2 will give me that wonderful x minus 3. That's exactly what I want to keep. And I'm actually going to write that on here. I'm going to point an arrow at that statement right there, and I'm going to say I want to keep that. The reason why I do that is for something that we deal with later on. When we deal with polynomials in higher degree than just linears, it's very important to point out what you want to keep because, well, you want to arrive at that. And so if I want to keep x minus 3, I'm going to divide both sides by 2. Remember, the absolute value of 2 is just 2. So I could move this 2 out front. It would still be 2 because the absolute value of it is 2. So dividing both sides by 2, and I should kind of stick with my idea. I'm going to put this out here. So let's see. All we did from here to here was we subtracted. We did arithmetic. I don't really need to say anything there. But we factored here. And then now we're going to divide both sides by 2. So that gives me the absolute value of x minus 3 is less than whatever epsilon I was handed divided by 2. And this is super important because we've arrived at what we want. We wanted to get the absolute value of x minus 3 being less than something. And notice we have that. That something happens to rely upon whatever epsilon neighborhood somebody handed me. So the smaller the neighborhood, the smaller my choice for delta, because this right here is now what I'm going to call delta. Again, because I want my absolute value of x minus 3 to be less than something called delta, and I've ended up at the absolute value of x minus 3, so I'm going to say that's strictly less than delta, where delta is equal to epsilon over 2. So let me rewind the tape a little bit. And sorry that my screen is a little bit fuzzy. I think I'm going to reset my wireless in a moment here. But for now, let's go ahead and continue forward. Now, with this scratch work, I've just assumed that I've arrived at what I wanted to end at here. And working our way backwards, just doing a little arithmetic and stuff like that, we have arrived at the fact that if we have made that assumption, if we've landed at this, then it must be the case through a set of implications, a chain of implications, it must be the case that the distance between x and 3 must be less than epsilon over 2. Now I can start my proof. And the proof, you're going to eye your scratch work the entire time. You're going to continually look back at your scratch work. You never ever submit your scratch work when it comes to submitting a proof. That is, unless you're doing it, let's say on an exam or something like that. But if you're going to formally submit a proof, like publish it or something like that, you would never show somebody your dirty work, your scratch work behind the scenes. You want to sound like a genius. And so what you do is you leave your scratch work at home after you've cleaned it up as a proof. So here we go. I'm going to actually hide that scratch work. I'm going to go ahead and go over and use this template. This is actually my template right here. And I'm going to start my proof. Proof. PF means proof, if you didn't know that. Now I'm going to say, here, I'm just stealing the definition. Now the definition I have written here, that's exactly the definition of the precise that's the exact precise definition of a finite limit at a finite point. It's a mouthful. So let's go ahead and use it. For all epsilon that is positive, So I'm not even telling you what the epsilon is. I'm not telling you epsilon's 0.2 or 0.005 or 10. I'm just saying no matter what epsilon somebody hands me, I will choose delta to equal. Now, I'm following this definition. I've already stated this part, and I'm saying there must exist a delta that's positive. Specifically, I'm going to name that delta right now. The delta that I'm going to name is the one that I found over on the right-hand side of our screen here. That delta is equal to epsilon over 2. Sorry, my screen is just doing that. I have no idea why. So I will choose delta equals epsilon over 2. Now let me continue forward in the definition. Now the definition says, once I've stated that I've found that delta, I then must state, well, as long as x is within a delta neighborhood of 3, specifically that delta neighborhood of 3, then we should be able to show that our function is within an epsilon neighborhood of 9, the epsilon that somebody else handed me. So here we go. I say if 0 is less than the absolute value of x minus 3 is less than delta. Notice I'm just stealing the definition. I literally have written down for all epsilon greater than 0. I've literally stated what delta is, and now I'm stating, well, if this is true, remember this is the if part and this is the then part. So if it's the case that 0 is less than the distance between x minus 3, which is less than delta, then, well, because we made the choice for delta to be equal epsilon over 2, so if somebody hands me an epsilon of 1, I'll choose delta to equal 1/2. Then I happen to know the distance between x and 3 must therefore be less than epsilon over 2, because that's what we chose delta to be. Multiplying both sides by 2. I'm just noting on the side here that I'm multiplying both sides by 2. I get this. I call this climbing the ladder. And the reason why I call this climbing the ladder is because really what I'm doing is I'm picking up right here and I'm starting to climb this ladder and rebuild until I get to there. So this is really where I'm going to be looking at my scratch work. Nobody else is going to see this besides my professor, but I want everybody only to see my beautiful proof. So I get over here and I say, well, I'm going to multiply both sides by 2. And somebody kind of nods their head and they say, okay, all right, I'm with you. And you say, well, but that implies that, are you okay with me distributing to it? And people nod their heads and say, yes. Okay, well, that implies that 2x minus 6 in absolute value must be less than epsilon. And people nod their heads and say, yeah, okay, all right, fine, whatever. And you say, and that implies the absolute value of 2x plus 3 minus 9 must be less than epsilon. And people nod their head. They say, yeah, okay, all right, I get it. And you say, but do you notice what I've just written? I have just written that the absolute value of 2x plus 3 minus 9 is less than epsilon, but 2x plus 3 is my function and 9 is my limit. 2x plus 3 is my function. Let me zoom in back here. And 9 was the limit that we were concerned with. So that means that what we have said is, if somebody hands me an epsilon, I don't even know what epsilon they're handing me. Somebody just walks in with an epsilon, I'm going to choose half that. For this specific function, I'm going to choose delta to equal half of that. And I'm going to say, so now let's get a real visual of this. Let me hop back over to my other screen. And what I'm going to do is I'm going to draw your attention to down at the bottom. Those are the x values that are on the bottom here. Okay. And somebody comes in and they hand me an epsilon. Now let's just make the epsilon easy here. The epsilon's a half. They've given me an epsilon of 1/2. So 9 plus a half, 9 minus a half, that's my epsilon neighborhood. And we are saying that if you hand me an epsilon of a half, I'm just going to let delta be half of that. I'm going to let delta be a quarter. Now notice my delta neighborhood right now, it goes 3 to about 3.75, and 3 down to 2.25. That's not a quarter in radius, so I'm going to decrease that until it's 1/4. And once I get to 1/4, that's exactly 1/4, by the way, you'll see that I have done it. And if somebody says, no, never mind then, I don't like the fact that you beat my game, I'm going to decrease your epsilon even further. I'm going to go down to an epsilon of 1/10. Let me see if I can get a 1/10 here. No, that's more than 1/10. There we go. I'm going to give you an epsilon of 1/10. Well, I already know by the proof, I'm just going to choose my delta neighborhood to be half of that. Half of 1/10 is 0.05, so I'm going to just decrease this to 0.05. And yet again, I beat them. So no matter what's beautiful about the proof is, no matter what epsilon they hand me, I will always choose my delta neighborhood to have a radius of half that epsilon. And if that's the case, I always lock in our function into the intersection of those two painted regions. Now going back to our work here, again, that's such an elegant and beautiful proof, and reading it in language is very hard to do, but I'm just going to say, no matter what epsilon somebody hands me or challenges me with, I know that choosing a horizontal neighborhood, a delta neighborhood, of that very small radius, epsilon over 2, you choose any x value from there, the y value, so this basically means, you would not put this language in the proof, but I'm just going to say this, write this for your benefit. Choosing an x value from the neighborhood 3 minus delta to 3 plus delta, where delta is epsilon over 2, will imply that the y value for that x value is in the neighborhood 9 minus epsilon to 9 plus epsilon. In other words, the y value for any x value in that delta neighborhood, that y value is going to land in the epsilon neighborhood centered at 9. Now remember, these are punctured open neighborhoods, so the one x value we cannot grab is the x value at 3. So this is a punctured neighborhood, so technically speaking, you would remove 3 from that. And that's because, again, x is not allowed to be 3, because if it were allowed to be 3, you would have that difference to be 0, and that's not allowed in the proof. We don't care about what the value of a function is at the limit. We care about the value of a function as it approaches that finite point. And that is a full epsilon delta proof. Very clean. Normally wouldn't have that green ink there, and as I may have mentioned in a previous video, I often write QED at the end, quod erat demonstratum, which means so it has been demonstrated. Now, there are a lot of questions that come up at this point about, well, will it always work so nicely? And you know, what can I expect if I face something on an exam, yada, yada, yada. Well, if it's linear, the answer is yes, it will always work this nicely. Linears are very clean. But once you graduate away from linears, they get a little uglier. But before we do that, let's do yet another linear. This time, I don't need to explain every step. Instead, I'll just do the steps. The very first few examples, actually pretty much all lectures, I still kind of repeat the definition, where we want to work in, what world we want to work in. So let me write that down. And I wrote it only slightly differently, just because it matches some of the language we use in our proof. For all epsilon greater than 0, there's probably a delta we can find that's positive, such that if the distance between x and a is positive but less than delta, then the distance between our function and our limit is less than epsilon. That's what the definition is. Now, we're going to start by saying, well, I don't know how we got here, so let's go ahead and work assuming that we've arrived there. So let's go ahead and move over to the side and start some scratch work. And I'll keep our actual limit in view this entire time. And by the way, you should always look at the limit you're handed and make sure it's realistic. If you plug in 5 for x, because you can do a direct substitution here just to check. If you plug 5 in for x, you get -5/3. If you add 1 to that, that's -5/3 plus 3/3, which is a -2/3. So this makes sense. So before I even prove it, I just want to make sure that it's true. Now we write our scratch work like any good mathematician does, and we're going to assume that our function is within the epsilon neighborhood of the limit L. And we want to show that the distance between x and a is less than delta. Now let me substitute in what a and f of x and L are in this situation. So we're going to assume, I'll put implications in there. We're assuming that the distance between negative 1/3 x plus 1, that's our function, and the limit, which is negative 2/3, we're assuming that that distance is less than epsilon. And again, we want the distance between x, oops, my pen messed up slightly, distance between x and 5, we'd like that to be less than some number delta. And note that distance between x and 5 is going to be positive because, again, x is never allowed to actually be 5. This looks worse than it actually is. Still the same problem we faced last time. So let's go ahead and clean this up. This will imply we have a little arithmetic, right? Negative 1/3 x plus 1 plus 2/3, so that's plus 5/3. And we know that's less than epsilon, so that's a little arithmetic there. If you look at where you want to arrive at absolute value of x minus 5. So I know that I can factor something off those two terms within the absolute value to get an x minus 5. You would factor off a negative 1/3. You'd be left with an x minus 5. It's good to see, honestly, that the algebra we learned with factoring all those years is paying off a little bit, very lightly here. By the way, that's just factoring. That's all I did there. Now, this one I'll take a little extra step just to showcase what I'm thinking. You should know that the absolute value of a times b is the same thing. Actually, let me give myself a little extra room for this. So the absolute value of a times b is the same thing as the absolute value of a times the absolute value of b. That is true. And so I'm going to say the absolute value of negative 1/3 times that x minus 5 is the same thing as the absolute value of negative 1/3 times the absolute value of x minus 5. Remember, I want to keep that piece right there because that's where we want to arrive. So we need to get that 1/3 to the other side. Luckily, it's an absolute value of it. So I'm just going to take its absolute value. Nothing big, that's just a 1/3, absolute value of x minus 5, less than epsilon, and then I'll multiply both sides by 3. And you get this beautiful 3 epsilon. They almost are mirror images of each other, aren't they? So I know that had I arrived at the distance between my function and my limit being less than epsilon, it had to have been done by assuming one thing. That delta is equal to 3 epsilon. Let me go ahead and draw that line there. Now that I know what delta is, because that's the whole goal with this is to, somebody hands me an epsilon, my job is to find the delta. Now that we found that delta, let's go ahead and use that delta in the proof. I'll refer back to this scratch work several times, but let's start building the proof only for the world to see. So given epsilon greater than 0, notice I'm not exactly copying the language because I want you to have the flexibility to speak in some other language than what I give you exactly, as long as the statement is equivalent, right? The definition statement here is for all epsilon greater than 0. What I'm saying is given an epsilon greater than 0. I don't know what epsilon is, so it's pretty much any epsilon. Let delta equal, well, what was our choice again? Oh yeah, our choice was 3 epsilon. If I move that screen fast enough, it's trippy. So I'll zoom in here and I'll call this 3 epsilon. Again, reading from my definition up above, if 0 is less than the absolute value of x minus 5, because that's what x was approaching as 5. If that's less than delta, well then, just because we know what delta is, we know that delta, by our decision, is 3 epsilon. So as long as the distance between x and 5 is positive and still less than delta, then distance between x and 5 must be less than 3 epsilon, because that was our choice for delta. Which will imply, now it's natural, I think, when people say, oh, I want to get epsilon on one side, they divide by 3 and they get, oh, 1/3 is, times the absolute value of x minus 5 is less than epsilon. Most people would actually stop right here and not know what to do if they didn't have scratch work. Luckily, I have scratch work. I can copy and climb this ladder. So after I have that 1/3 times absolute value of x minus 5 being less than epsilon on one side, I will then change it magically. And when somebody's reading this proof, they're gonna look at this and go, wow, what a genius. I would never have thought of saying the absolute value of I would never have thought of saying 1/3 is the same as the absolute value of negative 1/3. Wow, this person must have been doing math for a while. It has nothing to do with that. It has everything to do with my scratch work. Now I'm just going to I'm going to connect those two and distribute the negative 1/3 through. And this kind of showcases that you can skip every once in a while a step. So I'm sort of skipping from here to here, really. I'm just completely gluing them together immediately. So you could do that. It's perfectly fine. So this is going to be a negative 1/3 x plus 5/3. And somebody looks at that and they say, it might take them a moment to kind of see what we did, but then they go, oh, okay, yeah, I get it. And then the final step, again, looking back at my scratch, is that final step up there. I just break that to a negative 1/3 x plus 1 minus a negative 2/3. Negative 1/3 x plus 1 minus a negative 2/3 in absolute value is less than epsilon. And then I take a moment to actually tell the reader, this is my function minus my limit. Thus, given any epsilon, doesn't matter what it is, as long as I choose delta equal triple that number, then choosing an x value for my horizontal neighborhood of size 3 epsilon, or basically size delta, but it's 3 epsilon, I can guarantee its function value is within an epsilon neighborhood of L. Again, I'm going to say that with handwriting, even though you would not include that in the proof. It's so new to you, I want to say it again. So given any x value, not 5, because x is not going to be allowed to be 5, but given any x value that's not 5 in this delta neighborhood that we have designed, which is 3 times epsilon, that's centered at 5, the function value of x is in the given epsilon neighborhood about our output, negative 2/3. The visual is as follows. You can see I have the function up here, negative 1/3 x plus 1. We're centered at 5 for our x values, as you can see right here, and also up here in the app. And now somebody hands me an epsilon. Let's just say it's an epsilon neighborhood of 0.1. So that's the red horizontal bar there. Remember, our choice for delta will just be 3 times that. So watch this. 3 times 0.1 is 0.3. There we go. And by the way, you can actually choose delta smaller than that. Once you get a delta that works, tightening up that delta neighborhood is perfectly fine. You totally tighten up that neighborhood too. But generally speaking, we just lock it in this case, delta equals 3 epsilon. Good visual of this theorem. Or limit is what I meant to say. Now, honestly, there are so many things that you can do with the epsilon delta proof of a finite limit at a finite point, but right now we're just dealing with linears, right? Linear functions. And probably the best one to do right now is actually a proof of one of the limit laws. We have a ton of little limit laws that we were using in a previous section, but now we can actually prove some of them using the epsilon delta proofs. So this is the identity law, and it's actually a fairly simple statement. As x gets really close to a, guess what x gets really close to? A. There you go. So it's a simple statement to say, but let's see how it is to prove. Now this time, I'm not going to write down the definition. I'll just write down my scratch work. And maybe I'll divide out the board right now with green, since I have it right there. There's my board. Scratch work will be on the right hand side. And remember, when you're doing your scratch work, you want to assume at the end, you want to assume that you've arrived at the end of your proof. And the end of the proof is, hey, the distance between F and L is less than epsilon. So let's assume that we've arrived there. We want to show that the distance between X and A is less than some number, delta. Well, in this case, the function is actually X itself, and the limit is actually A itself. So I'm going to insert that into this piece right here. So this will imply the distance between X and A is less than epsilon. Oh, wait a second. Isn't that what we wanted? Distance between X and A is less than something? Yep. This limit law is incredibly fast to prove. We have just shown that, well, we want to keep this because that's where we want to arrive at. But guess what? We've already isolated it. It's already absolute value of X minus A. So I guess we're just going to allow delta to actually equal epsilon. My scratch work is done. So now I'll go over to the proof itself. Proof. Notice I'm trying to keep it without moving my screen here. Now I'll use symbolic logic. For all epsilon greater than 0, let delta equal epsilon. Well, since epsilon is greater than 0, so is delta. Right? If the distance between X and A is less than delta, then, well, the distance between X and A is less than delta. What can I say? And it's so, therefore, it must be less than epsilon. But X is my function, right? And A is my limit. Done. Again, the first statement right here just says, hey, as long as I grab an X from that delta neighborhood, its function value has to land within an epsilon neighborhood of our limit, period. That was a very fast proof. I know, don't blink. It happens very quickly. So the idea of proving is really to make sure you know how to master working your scratch work first. Just assume the antecedent, the end, and work your way backward to see what that delta was, and then start your proof. Again, you will give this scratch work to your professor along with the proof. But honestly, in real world proofs, you're only going to let the world see that black ink, which I forgot to write QED, so that I'm going to write that in. Because that is the stuff that people look at and they go, wow. And you're not trying to, like be the wizard behind the curtain or something like that. But the reality is a lot of mathematics is about succinct statements, making a beautiful, elegant proof without a lot of fluff. And in fact, there's a lot of steps in this proof that most mathematicians wouldn't even write, but we write it here because we want you to show your work initially. As you move forward in mathematics, you can condense this down even further. All right, so that is the video on proving finite limits at finite points for linear functions.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.